Right. Good afternoon, everyone. Okay, just give me a moment. All right. Yeah. Okay, guys. So two modules to go. So module 6 is another short one. Even shorter than yesterday's module. So did we even finish yesterday's yesterday's module? So yeah. So this one is going to be a quick one. Hopefully we'll get to start with module 7 as well. And yeah, I know we still have to go through the memo of the test, and but yeah, I just want to get through the work as well, especially module 7, because yeah, it's actually kind of an important one. So yeah, so let's get moving. Right, so for module 6, generation and supply of AC power. So this is pretty much just a read-through module that you guys can just go through. There is a little bit of general knowledge on this as well. So what I would recommend, and this is a bit of a place where the department can ask terrible questions. One of which is, which has happened before, is that they can ask you to name um, some coal-fired power stations from Eskom, or ask you to name an example of a hydroelectric station in South Africa, or anything of that nature. Problem is, those stations are not mentioned in the textbook, so yeah, so you guys will have to find those names somewhere else. So I am going to share um, basically a Wikipedia page with you guys. List of South African power stations. Now, I would recommend you guys go pick a few power stations, maybe 3 or 4 coal-fired power stations. Learn their names. Like, yeah, but try and pick, for instance, Eskom owned power stations, because those would probably be the ones that they are looking at. But in any case, yeah. So basically, what we're going to take a look at is the supply of electricity, what it entails, high voltage transmission, AC transmission systems, and we're going to also take a look at some feeder networks as well. Right, so before we go on with this, I just want us to quickly take a look at that list, just show you guys real quick. So yeah, so it gives you a little bit of information on how South Africa's power generation, or power, yeah, so basically our whole power fleet is composed. So basically we mainly use coal to generate power. And the funny thing is, this is the total capacity on the books. Eskom itself has a total capacity of 48, or potential capacity of 48 megawatt, which they cannot generate anymore. The reasons. So if we take a look at here, so there are actually quite a few here. So you guys will see for coal, yeah. So the first bunch of power stations of coal power stations. So just look at the operator and you'll see Eskom. So there's actually quite a few. Kusile being quite a recent one. There's Kendall Power Station, Komati Power Station, Hendrina, Grootvlei, Duva, Arnott, uh, Medupi, Matla. So there's actually quite a few that you guys can take a look at here. So I would say pick 4 or 5 and just know those names. Yeah, so there's also the Letabo Power Station, just I think this is just outside Vereniging, or between Vereniging and the Val Dam. But in any case, Then there's also open cycle gas turbine power stations, so not a lot of them. So these are power stations typically used just for actually more in case of well, if capacity is not enough. So these power stations nowadays run 24/7 with load shedding. Then we have natural gas, and then there's also pump storage. So this can also, I think, yeah, this was also asked once as well. So there are 3 ESCOM pump storage schemes. And then hydroelectricity, also a whole bunch. So I also would say pick maybe a few ESCOM ones here. In fact, the ESCOM ones, they're not many. Uh, so yeah. So basically pick 3 or 4 here and just know the names. And then there's also, well, South Africa only has one operational nuclear power plant. So yeah, and that's Kuiberg. And then we also have some, yeah, so South Africa has some wind farms as well. Uh, if we take a look at here, at the operators and owners and developers, not really, yeah, Eskom doesn't have any any wind power stations really, except for Klipjewel, which is also dismantled. So why did I click there? So yeah, so which is also dismantled. And we also have concentrated solar. Again, this will be private ownership, so I don't think this will ever be asked. Then we have solar photovoltaic. So there should be, I'm not too sure if there's a, see, I don't think there is an Eskom owned one here. Yeah, but I would maybe look at one of the ones with the biggest capacity and then just know that one. But yeah, but for now, I would say the most important here would be nuclear, hydroelectric, and coal. You guys to know. So yeah, but other than that, so there are some others here as well. So landfill gas is mainly municipal. Then we also have biomass power as well, also mainly municipal or oh yeah, you guys can actually see the sugar, the paper mills and sugar mills basically making use of biomass power. Right, so basically the byproducts or the waste that they generate, they use to generate power. Okay, okay, and then that's that. Right. Oh, okay, cool one. That's actually quite awesome. I myself never been there. I can imagine it's quite the sight. All right. Okay, so yeah, so you guys can actually, if you go look at that list of power stations, um, most of them you guys will see are quite a ways away from their centers of consumption. So except for maybe 1 or 2 of those power stations. I know, for instance, the power station in Pretoria West basically sits in Pretoria. I don't know that. Yeah, the thing is, I don't know if that power station is still operational though. But I have been told that it is still in operation. So, but rarely see it operating. But in any case, now there's a reason why we build our power stations away from our points of consumption. For one, there's quite a few economic considerations. So this would be, if you guys look at most of the coal power stations, a lot of them are built pretty much right next to or on top of the coal mines. And this is just to reduce the amount of yeah, just to reduce the amount of transport or logistics that go into transporting coal from the mine to the power station. So ideally, you would have a conveyor belt, if you can, just running from the mine into the power station. So yeah, so you want to eliminate that transporting costs. Now, in South Africa, for some reason, I think we all probably know the reason, but for Eskom, so yeah, so not just Eskom, so quite a few of the municipal power stations as well. Coal used to be transported via rail to to a lot of these power stations. These rail lines have been all left in disrepair, haven't been maintained, so it's now done with trucks burning, burning diesel and petrol, which is a way more expensive fuel source than coal, driving up the price of coal even more. But in any case, so yeah, so there's also pollution considerations. So just imagine with a power station sitting inside a city, my goodness, yeah, it's already. I know in Pretoria West, for instance, you also have Pretoria Portland cement as well, and yeah, in the manufacturing of cement, there's also a process, a burning process as well that happens, and goodness, and it generates a lot of ash that actually just goes and sits on everything, and it's not just locally around the factory or around the power station that you would get it. I mean, if you have strong winds blowing as well, it will carry that ash quite a ways away from the power station. And then water. Now, if you guys go look at how a power station functions, especially things like coal power stations and nuclear power stations, um, they still need water. Um, Basically, use water to make steam from the, yeah. So in the case of a coal-fired power station, by burning the coal, uh, heating the water up till it becomes superheated steam, and that steam is then used to drive turbines. Same thing is done in nuclear power stations as well. So basically, you have your uranium fuel rods being left to undergo nuclear, yeah, so basically a nuclear reaction, and then that generates a significant amount of heat, again, used then to heat up a whole bunch of water to superheated steam conditions, and then that's then used again to drive turbines. And then logistics is also an issue, so we actually kind of already touched on this. So in olden days, they used to use trains to cheaply transport coal between power station or between the mines and power stations. So yeah, so that's also part of the consideration there. And the other thing is you also don't want trucks, and yeah, so heavy trucks can damage the roads inside a city. Yeah, it's just a mess. All right, so if we take a look at our transmission voltages, so you guys also note that when we transmit electricity from the power stations, it's usually done at a very high voltage. And yeah, so this is something that Eskom is actually supposed to be doing, but they're not, for a power generating company, they're not really good at it. It's basically to adjust their transmission voltages and supply capabilities to meet escalating demand or increasing demand. So yeah, so the demand for electricity is higher every year. And yeah, so in order to meet that demand, usually what is done is we transmit voltages, or rather transmit on the grid at higher voltages, usually to keep the costs of installing new transmission lines low, because it means higher voltage, less current. And yeah, and we also try to lower the impact of the increasing supply of electricity as well. So we kind of it's quite the balance. So we need to basically keep up with the demand, but we also mustn't, go ahead and build, hundreds of gigawatts of generating capacity while only a small portion of that is used. That's a bit of a balancing game that we need to play there. Right. So if we take a look at high voltage transmission now, at your power station, you guys will actually be surprised at how low, at some of these power stations, how low the voltage actually is. So we usually generate our electricity at a low voltage, and then at a substation part of the power station, we then step up the voltage for transmission. Now this is, yeah, so again, this is usually done to keep the amount of current flow um, low on the transmission network. So if you step up the voltage, the current comes down. And yeah, so this is typically, yeah, so transmission voltages would be anything from 132 kilovolts up to, yes, Eskom, I think Eskom has one of their transmission lines are actually more than 600 kilovolts. So yeah, so it is actually quite a, so it depends on the distance that you need to transmit the voltage. That's then going to depend on what voltage you're going to transmit at. Right, so then at your points of distribution, we step down the voltages again. And yeah, so basically, as I explained earlier, you have reduced current flow when you have the voltage stepped up to a high voltage. And that then means that we can use thinner conductors, and that actually makes our transmission lines cheaper and much lighter than it would have been otherwise. And this in turn then means, because we're using less conductor and a lighter conductor, we can actually build less pylons, basically having them built further apart from each other. Um, so yeah, so there's actually quite a few things that add up to the cost of building a transmission line. There are, however, some disadvantages with stepping up the voltage or transmitting voltages or transmitting at high voltage. For one, it requires higher insulation properties. So basically what this means is you have a minimum distance that your conductors need to be at from each other. The mounting points on your pylons also need to conform to certain specifications. So for instance, so if you guys look at your high voltage power lines, they usually, where the power lines are resting on the pylons, you have massive insulators providing the insulation between the pylon and the conductor so that there's no arcing taking place to ground. And then lastly, it's just plain dangerous. So so yeah. Yeah, so those are the disadvantages with high voltage, but the advantages or the benefits just outweigh the disadvantages immensely. So we are willing to work with those disadvantages. So on our transmission line, well, and actually a large part of just distribution networks as well, we make use of three-phase power. And yeah, so again, as explained, rapid development pretty much imposes increasing demands for electricity. So yeah, so as South Africa's economy grows, that's just gonna put in more and more demand on the electricity supply and on the transmission network, which is not, yeah, so needless to say, Eskom is failing at meeting demand there. And yeah, so this also then leads to increasing transmission line voltages as well. So remember, um, more load or more demand also translates to higher currents. So in order to keep the current low, we need to transmit at higher voltages. So there is a bit of a problem here, um, especially if we have power stations very far away from their points of consumption. And yeah, so sometimes what we also do is if we have loads bigger than 60 megavolt amperes in a small area, it's usually more economical to, well, economical in capital and land. So remember, you need land space for substations and transformation losses to step down directly from 132 kilovolts to 11 kilovolts. So if we take a look here, this is basically our secondary transmission. So maybe between cities, um, you have 132 kilovolts, and if you step down to 11, so 11 kilovolts, you actually already have consumers at that level. So usually factories and mines, right? Now, our transmission and distribution networks radiate in various directions from different power stations. So it's sort of, yeah, so it's sort of, if you look at a map of South Africa, I don't know if Eskom, I can't remember if I ever found this. I want to see if there is something like this, a map of the South African grid. That would be interesting. Okay, cool. I think I did find something, but this is basically the main transmission lines. Let me maybe show you guys real quick. But this is now not just, yeah, so South Africa it's not just dependent on South Africa itself for power generation. So, yeah, maybe I should just zoom in here. So South Africa is also dependent on other countries as well. So Mozambique, for instance, there's the Cahora Bassa hydroelectric project as well that feeds South Africa as well. So you guys will see there's actually quite a few transmission lines, and the thing is, South Africa is actually involved in these other countries' electrical networks. So yeah. So we tie in. So for instance, here in Namibia, for instance, as well, we are tied in there. In fact, if I'm not mistaken, this transmission network from Ruakana going to South Africa, this is actually a DC transmission line, and one of the ones, I think it's this. Yes, actually, I see here now. From Mozambique, you guys will see there is a 533 kilovolt DC transmission line going from there to Pretoria. Right. And this DC line actually terminates just outside of Rietvlei Dam by what is the power station's name? Apollo substation. Yeah, so we have then our primary feeders that are interconnected at grid substations. So basically at your substations is where you have basically the scattering to, different towns, different cities. And yeah, this all then will form part of your national grid network. Okay, so one of the ways we can feed a grid, or rather one of the ways feeders can be organized is what we call a radial feeder system. So you will have your grid substation at the center of this kind of network with feeders going out to different distribution substations. Right, so in this manner, um, basically, yeah, so yeah, so if you have, let's say you have a hospital on this network here, you can maybe put up a double feeder for that substation. But the drawback of the system is if one feeder fails, then the whole part of this is then, without power. And yeah, so there's another drawback to this kind of system is that if you are already in a built-up area, doing this is a bit difficult to have the grid substation at the center of everything. But I mean, it can be off to the side and just feed different areas individually. Yeah, I don't know what there's not really any cost saving to this. This is actually kind of a outdated way to um, do transmission and distribution networks. Then you have a ring feeder system. Now, ring feeder systems, so you have your grid substation, so you might have your national transmission line coming in here. So instead of having the substations all branch off of the grid substation, we form a ring that the grid substation forms part of. Now, if you have, let's say, for instance, this feeder here fails, then you still have the other feeders that can feed into these two other substations, keeping the power on. So this has quite a bit of redundancy in terms of protecting against power failures or cable failure. There's a drawback to using a system like this though. It does have a higher initial capital cost, but it does have lower power losses, and this is also a more popular method of distribution and transmission networks. And yeah, so then actually for both ring feeder systems and radial feeder systems, we can account for the variation in voltage drop due to load changes by using a tap changer or tap changing transformer at our power station. So yeah, or tap changers. So basically what you effectively doing is, as the load increases or decreases, you adjust the voltage level by adding or subtracting turns on the transformer. That's what you're essentially doing with a tap changer. So adding turns to the secondary side will step up the voltage a little bit, and taking away turns will bring the voltage down a little bit. So it's usually within like a percentage range that you do this. It's not going to be a drastic change in voltage. Right. Okay, and then guys, that's it for this chapter. So yeah, that's pretty much it. Short chapter, really quick. And yeah, so let me just put this up for download. I see I completely forgot about it. And I'll put up chapter 7 as well. And we can continue with chapter 7 today.